I know what you're thinking. That angle-angle similarity postulate was so useful and made it so much easier to prove that triangles were similar. Why don't they have more shortcuts like that? Well, they do. Today we're going to learn the other two. There's only 3 total, and the other 2 are called side-side-side similarity theorem and side-angle-side similarity theorem. Now you'll notice that side-side-side is a little different from the side-side-side congruence postulate, so pay attention to the difference here. Again, obviously it's not going to be that we have 3 sets of congruent sides, because similar doesn't mean same shape, same size. Similar just means basically same shape, different size. And if we knew nothing about the angles of these triangles, what we could do is we could compare the ratios of the corresponding sides. And if those ratios are all equal, then we would know the triangles were similar without even checking the angles. Remember, the definition of similar polygons means congruent angles and proportional sides. Here our shortcut is that we just have to check that we have proportional sides. But guess what? That only works for triangles. I've got one more that only works for triangles. It's called side-angle-side similarity theorem. Here you only have to check 2 ratios, one side to one side, the other side to the other side. And if those are proportional, and if the angle between those, if the angle where those 2 sides meet is congruent to the corresponding angle where the other 2 sides meet, then we've got similar triangles. So we're checking to make sure that we've got an angle that's congruent and 2 sides that are proportional. Let's do some examples. I've actually got 9 examples for you today. Here's number 1. Is either DEF or GHJ similar to ABC? So we're going to check to see if this one or this one is similar to this main one right here. And you can probably already tell that we're going to be relying on side-side-side similarity theorem since we're given the lengths of all the sides. This example is extra tricky because those other triangles are rotated and flipped. So you have to rely on that tip that I gave you where we compare the shortest sides to the shortest sides, the longest sides to the longest sides, and the remaining sides to the remaining sides. Here's what I mean. If we were checking out these 2 triangles, let's check the shortest side from the first one and the shortest side from the second one. And the longest side from the first one and the longest side from the second one. And the medium length side from ABC and the medium length side from DEF. And the question is, are those sides proportional? And I discovered they're not proportional. They reduce to, well, 2 of them are proportional, but that third one is not. So since we don't have proportional side, 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 we would say that these are not similar. Well, I really hope it's these 2 then. Let's check. We'll take the shortest side from ABC and the shortest side from GHJ, the longest and the longest, and the medium and the medium. Did you notice that like the right side of this one matches with the left side of this one? That's why I'm saying it's a little bit tricky. The 8 matched with the 16. So it's almost like that triangle was reflected. But now we're checking this out to see how these reduce, and I do get a 1-to-2 ratio for all 3 sets, and so we can say that all 3 sets are proportional. If all 3 sets of sides are proportional, then we found our similar triangles. Triangle ABC is similar to triangle GHJ. I want to double check to make sure that that letter order is correct. Was side AB supposed to match with side GH? AB with GH, yes. And was BC supposed to match with HJ? BC with HJ, yes. So it looks like all the correspondence is in the correct order. And so we answered the question using the side-side-side similarity theorem. Next example, find the value of x that makes these triangles similar. Well, if these triangles are going to be similar, we know their sides have to be proportional. And since they gave me the similarity statement, I won't have to think about shortest to shortest, longest to longest, because they've already given me the correspondence. I know that I'll match my AB with my DE. Let's start setting that up. The AB matches with the DE. So it looks like nothing funny, no twists, turns, reflections. The BC matching with the EF. And the AC matching with the DF. And now since they already told me that those triangles are similar, I can assume that all the sides are proportional. I can throw those equal signs in there. And then I just need to solve for x. Again, how do you solve cross multiplying when there's two equal signs? You don't. You just pick a part that you want to solve. I think the worst two that I could pick are this one and this one, because when I start cross multiplying, I would take an x thing times another x thing, and that would wind up being quadratic. And if I don't have to, I'm going to avoid that. So I think it would be nice just to pick these two to start out. I'm going to cross multiply, takes the x minus 3 times the 10 and the 4 times the 20. Remembering to set those equal to each other. I'm getting that x equals 11. Let's check that back in the x minus 3. 11 minus 3 is 8. 8 over 20. What is that? Well, that's definitely the same thing as 4 over 10, right? So that's a good sign. And you know, if x is 11 for that fraction, x is going to have to be 11 for this one too. 2 times 11, 22, plus 3 is 25. How are you feeling about 10 over 25? Divide by 5, divide by 5, that's 2/5. And so is this one. And so is this one. So I think x equals 11 is the winner. Example 3, are these triangles similar? I'm seeing that bow tie right away, so I know that I have at least one set of congruent angles, those vertical angles. This is actually set up in sort of a side angle side formation, right? But just because it's set up in side angle side doesn't mean they're similar. I still need to check to see if those sides are proportional. So on this first triangle, I'm going to take the shortest side and compare it to that shorter side on the second one. And then I'll take the 18, that longer side, and compare it to the 24. Great news. Those two sets of sides are proportional. Now I only have two sets of sides, but luckily I have the angle that's between them congruent. So I can say yes, those are similar by the side angle side similarity theorem. This next one could be a little tricky if you didn't have my tip about shortest side to shortest side. So on this first triangle, shortest side is 28. On the other triangle, shortest side is 16. Then I'll switch to longest side from the first and longest side from the second, and medium length side to medium length side. They're proportional. We have three sets of corresponding sides that are proportional, and that's enough. I don't need to check the angles anymore because I've got a little something called the side similarity theorem. Example 5, find the value of m that makes triangle ABC similar to triangle DEF. And they give me a bunch of lengths and I can't even handle all this, so I'm going to draw myself a picture. Honestly, I don't even know which triangle is bigger, so my drawing probably won't be to scale, but I'll label this first one ABC, and then making sure that I use the same order that I went in there, I'll call this one DEF. So sketch yourself a picture and then start filling in those lengths. It says that AB is 3, BC is 4, DE is 2m, EF is m plus 5, and angle B is congruent to angle E. Great to know. Looking like a side angle side setup there. And I'm looking for a value of m that forces those two to be similar to each other, meaning that that 3 would have to match with the 2m in the same way that the 4 matches with the m plus 5. What m value will do that? Let's solve for it. Now on this side I distribute the 3. Do you know why I don't have to distribute the 4 on this side? It's because there's no plus sign in here. You don't distribute when your inside stuff is multiplied. 4 times 2m is the same thing as 4 times 2 times m, and 4 times 2 is 8. No distributing unless you saw a plus or a minus sign. I'm getting m equals 3. Let's go stick that back in and see if it makes sense. 2 times 3 is 6. 3 plus 5 is 8. And that's totally making sense. Do you even see what the scale factor is? Scale factor of times 2, isn't it? Number 6. Do you even see the 2 triangles here? Here's the first triangle. And the big one will be our second triangle. Unless you're feeling really advanced, I would definitely recommend to draw both of those out. This little one isn't so bad. This is just a 4, a 6, and a 5. But for the big one, you have to do a little math, like this PS is going to be 4 plus 8, 12. And PR, 6 plus 2, 8. And then RS is that 10 down there. I just think drawing it out makes it way less stressful. So now I'm going to take the shortest on this one to the shortest, and the longest to the longest, and the medium to the medium. And those are all reducing to 1/2, so I have 3 sets of proportional sides. So yes, those are similar by the side, side, side. Similarity theorem. Example 7, looking like a bow tie, yeah? Which is making me think I've got a side angle side set up for both of those triangles. Remember that I want to take the smaller length and match it with the smaller length. And maybe you can see that this is a 2-to-1 relationship. Remember that another way to do this is to take 7 divided by 3.5, and that comes out to 2 on the calculator. 8 divided by 4 also comes out to 2. Those are both 2-to-1 ratios. So we've got only 2 sets of sides that are proportional though. They didn't tell us enough to figure out all 3 sides. But luckily we had that angle that was included between those congruent to the other one. So 2 sides proportional and the included angle congruent means that yes, these would be similar by side angle side. Number 8, checking to see if triangle ABC is similar to, it's gotta be this one down here, right? They'd have congruent vertical angles. I feel like I can do that bottom triangle the best. So like I said, we had those congruent vertical angles on those 2 triangles. Do you see the parallels? I'm looking at you, parallels. Parallels can give me congruent angles too. Do you see the Z shape right here? I could say that this angle B up here and this angle D down here are alternate interior angles. And you know, technically, a backward Z would give me these angles congruent too. But who needs that when you have, do you know which one I'm going to use? Is it AA, SSS, or SAS? Those are the only 3 we have to choose from. And you probably realize this one is an AA. I found 2 sets of congruent angles, technically 3, but all I needed was 2 sets of congruent angles, and I can say that those are similar triangles. I like having the angles marked because it makes it easier to find the correspondence. Which angle goes with the A? That would have been the E. And with the B, that's our double swoop, goes with D. And the C was our single swoop, our vertical angle, C. So it's nice and easy to check the order for that second triangle as well. Okay, love example number 9. Usually you're trying to find the height of the tree and you're depending on shadows, but what if it's a cloudy day? So this lady, she's just got a mirror. She places it on the ground and she walks away until her eyeballs can see the top of the tree in the mirror. Little science involved here. The angle of incidence equals the angle of reflection. So I've already got a set of congruent angles there. And also, since she's standing nice and straight up and down, and so is the tree, I've got another set of angles, those right angles, that I could look at. So when I look at the triangle that she forms with the ground in the mirror and the triangle that the tree forms with the ground in the mirror, I know that they're similar triangles because of angle, angle. And if they're similar triangles, then I can set up a proportion. I would know that the sides are proportional. So I could take the shorter length from the lady and the shorter length from the tree, the longer length from the lady and the longer length from the tree, and I can solve. And the height of the tree is 22 feet. I hope that helped, just seeing a ton of examples, making sure that you're checking for those proportional sides this time. And don't forget that we still have angle, angle.